Hello and welcome to episode number 14 of CS350 Online. I'm your host, as always. I'm not sure who I am today. So on today's episode, we are going to continue our discussion of multi-level paging, and then we are going to talk about TLBs, which we're going to use to improve the performance of multi-level paging, and then after that, we will start talking about how OS 161 does its virtual memory and why free does nothing. But first, instead of OS of the day, I have spooky OS stories. So, 3 short stories then, shall we do? Whoever said OS wasn't involved with some kind of horror, right? So, as I'm sure many of you know, some computer systems get very, very overloaded with many, many processes. And high priority processes come in constantly. They're always coming in. But whatever happens to those low priority processes, the hello worlds? What happens to them? Well, sometimes, in some older systems, those low priority processes might be run eventually, maybe at like 2 a.m. on a Sunday when nothing else is around. Or maybe the computer will crash before those low priority processes ever get a chance to run. Now, the rumor has it that on the old IBM 7094, so you're looking at like the 60s, and when that started coming out, late 60s. But in 1973, when they finally decommissioned and shut down their IBM at MIT, they found low priority processes that had been started in 1967 and still hadn't run. So there's some professor out there who started a research job in 1967 and he's been sitting in his office for 6 years. And his job still hasn't completed. I thought that was funny. Here's another horror story related to an OS. So, some of you may have heard that over, there's been a number of satellite launches that haven't exactly been successful. A lot of the times when they're not successful, but it's like due to weather. But in 1996, June 4th, the Ariane satellite launcher actually exploded after it blast off. And the reason why the launcher, which is the big rockets, why they ended up exploding was, it was a malfunction caused by a faulty software exception system call that was the result of a bad 64 to 16-bit integer conversion. Caused the explosion. I think it was a loss of $500 million. And here's another one. There are many spooky tales from operating systems. So in 1985, there were 7 deaths for cancer patients that were actually attributed to overdoses of radiation treatment. That was the result of a race condition between concurrent tasks in the Therac 25 software. Race conditions can be very deadly. All right then. So, where were we last class? That's the good question. Not processes, that's for certain. No, we were in our last class talking about multi-level paging. And as part of that discussion of multi-level paging, we mentioned that we really wanted each level of the page table, or the hierarchy, to live, each individual tree, on one single page. And the reason, while may not be so apparent now, is because that's going to come in very, very handy for when we're doing on-demand paging, and it's going to improve the performance because the size of data that we usually load from the disk is usually a page-sized thing. So if the page table is 1 page, and that's the size of a load from disk, it's going to work out better in the long run. And we'll talk more about that another day, not today. So we have to figure out how many levels that our page table is actually going to need to be. And we gave you the formulas for that in our last episode. And what I'd like to do then is, before we get into talking about the performance of multi-level paging, I would actually like to do a sample problem. Now, we've skipped a few sample problems, and that's okay. There is, for those of you that are interested, there is in the folder or the zip file that I've posted to Piazza, you'll see one called paging. This is single level paging. And I'm not going to do that one, but if you want to do it on your own and post your answers to Piazza, by all means, I'll let you know if you're right. What I want to do today is multi-paging. So here we go. Here's our multi-paging. I'm going to make this wide. Put that there. And then we will bring this up. Look, it's all the formulas from last day. So let's bring up a new page. All right. Just can't see the questions now. So if you're following along at home, we're doing multi-paging. So let's look at our problem setup. So we have a virtual memory system that uses multi-level paging. Our virtual and physical addresses are both 64-bit. So we're going to say P equals V equals 64 for bits. Now our page size isn't 4 kilobytes here. Our page size is actually going to be 1 megabyte, which is 2 to the 20 bytes. And we're going to represent things in bytes. All right, so the first question then asks, how many bits of each virtual address are needed to represent the page offset? Well, if you remember, the page offset, the number is only related to the page size. It's the address within the page. So the number of bits we need for that is going to only be related to the page size. So for question 1, we get the page size, or the page offset, bits, is equal to the log of the page size. And if we do that, we end up with a log of 2 to the 20, which is, of course, is going to give us 20 bits. Spooky. All right. That's not so bad. Remember, before we introduced the ability to use logs and counting bits, you would have had to have divided the virtual address and done modulos of the virtual address to figure this out. But luckily, we know how we have this simple calculation here to do it. Okay, the next question is, what is the maximum number of entries in an individual page table? Well, so we know that each individual page table has to fit on a page. Then the question becomes, what is the size of the page table entry? Well, the page table entry, according to the problem, is 2 to the power of 4 bytes. So the number of PTEs per page is equal to the page size divided by the PTE size. And here we have 2 to the 20 divided by 2 to the 4. So we get 2 to the power of 16 entries per page. Now, if you're wondering about all these formulas, if you, again, go on Piazza, you will find that there is a virtual memory guide. And in that virtual memory guide, you will actually find all of these formulas and examples of how to use all of them. So that should be very helpful for you. All right. So the next question is, what is the number of levels we were going to need to represent this page table? Well, in order to figure out how many levels we need, we are going to need to figure out how many bits we need for the page numbers. So we're going to call it number of page bits is equal to the log of the number of PTEs per page, which we just computed to be 2 to the power of 16. So this is the log of the power of 2 to 16. So we need 16 bits to index each table. Now that we have that information, we can actually go about and figure out how many levels. And if you remember, we gave a formula for that as well, but there's many other ways you can arrive at the same number. So our levels, we do not have to convert bits to bytes because we're computing how many bits we need to index the page table. And remember also that we do not address individual bits, we address bytes. Question on Twitch there. So the number of levels is going to be the ceiling of V minus the page offset bits divided by the number of page bits. So what we end up with here is 64 minus 20 divided by 16. And so, of course, what you're going to get which is going to give you the very spooky answer of 2.75, but we can't have 0.75 bits, hence why we need the ceiling. So we need 3 levels for this page table. Now you might be wondering, but we didn't need all these bits, so what do we do with the extra? Like, how are we going to do that? That means that there are some parts of a page table that we wouldn't technically have filled, and that's actually okay. So one of the things that a lot of people actually do, oh, I love you, OneNote. You're such a great program. So what we're going to do is, if you look at your address, this is going to come in handy here in a minute. You've got your 20 bits down here for your offset, and then we're going to take 16 bits for this level, 16 bits for this level, where there's 32 bits. So whatever bits are left over, which I believe is 12, that's what we're going to use for the directory. Now, I've seen different ways of organizing this. Sometimes people will evenly distribute the bits between each level. For the purposes of this course, we're not going to ask you as to what the bit distribution is. We are always going to assume that if we need to have a page table with fewer entries, which, by the way, that's totally fine. The page tables simply can't be bigger than a page. They can be smaller than a page, but they can't be bigger. So I, by default, put the smaller entry in the root. That's just what I do. But if we want you to do something else, we will let you know. All right. Now, there's like a hidden instance of OneNote running, which is causing me a very big problem. Now let's look at the last question here, and this one is particularly interesting. This question asks, suppose that a particular process only uses 128 megabytes of space. That's 2 to the power of 27 bytes, which will come important to know that in a minute. Now, if that's the case, and that address space occupies the address range from 0 to 2 to the power of 27 minus 1, we want to know how many individual page tables at each level exist, and how many valid entries will be in each. Now, this problem seems very tricky, but I want to show you a way of thinking about it. So here is our address. We know that these lower 20 bits are going to be, of course, our offset, and that's not going to change. And then we organized it such that there were 16 bits here, 16 bits here, 12 bits here. Okay. Now, this is our address. These are our high order bits, and these are our low order bits. Now, if my address space is only using the lowest addresses from 0 to 2 to the power of 27, then I know that the only non-zero bits are the lower 27 bits. So in my address, only 27 bits are non-zero. And of those 27 bits, look, 20 of those bits technically are just the page offset. They fall into that range there. Which means, so we've got my 20 bits here, and my remaining 7 bits are going to belong to page numbers in third level. So, only 7 bits of this page number are non-zero. That means that all of these bits are 0, all of these bits are 0, and all of the 9 other bits here are all zeros. So, we always have one root, but how many valid entries does this table have? Well, how many valid addresses for this address space do we have? Well, I know that they are all the valid addresses for my address space have the highest order bits, all zeros. Which means that there's only one valid entry in my highest order table. Then in the next one, since all of there's only one table at the next level. And the reason why there is only one table at the next level is because there is only one root, and that one root table has only one valid entry. So there could only be one table at the next level. And since all of the bits for that address are going to be, all of those page numbers for valid addresses are also 0, I know there is only one valid entry there. So, one table with one valid entry means that there is only one table in the final level. And how many valid entries are in it? Well, 7 of these 16 bits are not 0. So we have 2 to the 7. So there you go. That is how many tables will exist at each level and how many valid entries will be in each table at those levels. And hopefully you can see here maybe how we do it. But if you want another example, try for, let's do 46 bits instead and see if you can figure out how that would work. I don't know about you, but I can only watch that for about 10 seconds before I feel incredibly nauseous. All right. So let's go back to the notes then. So we know how many levels there are. We know how to compute that. And let's just do a brief review here of the roles of the kernel and the MMU. So if you look at the kernel, it doesn't get involved with every translation, but it is responsible for managing everything. So it's going to manage the MMU's registers, which happens every time there is a context switch between different processes. So it doesn't necessarily happen for every thread context switch, but every time you go from a thread that runs in address space A to a thread that runs in address space B, we'll have to have the kernel update the MMU with new register values so it can perform the correct translation. We're also going to use the kernel to manage and to create all page tables or whatever data structures we actually need to implement our virtual memory translations. And we will use our kernel to actually perform the allocation and free of any physical memory. So that's all handled by the kernel. And then any exceptions that are actually raised by the MMU, those will also be handled by the kernel. So the kernel does a lot of management work, but the MMU does the per instruction level translation. So it's translating every virtual address to a physical address, and it's going to check and raise exceptions, but it doesn't try to figure out why. So now let's actually talk about a bit of a problem that we have. One of the little problems that we actually have going on here is the fact that if you have multi-level paging, or even page tables in general, for every instruction, in order to get the page table entry, you have to go from the CPU to RAM. Now, this is normally where I would walk across the room, but to be honest, I don't feel like getting up. But here's the problem. So you've got, if this is your CPU here, and you're doing an address translation, you need to get the page table entry. So you walk over to RAM, and you get your PTE, and then you have to walk back. And you have to do that for every single instruction that's executed, at least once. Sometimes, because loads and stores are very common, you're probably going to have to do it on average twice. Or at least the average is approaching to. Now maybe that's a lot of memory access. Remember that memory access is slow because you are leaving the CPU. Traveling across a wire is not free. So, let's think about things in another way. Let's suppose we have an array in C. Do you remember arrays in C? Arrays in C are stored in a contiguous block of memory. So if I create an array of 100 ints, I know that the address of the 10th integer is going to be the start address plus like 10 times the size of int. That's where it is. So the array is stored in a contiguous block of memory. So if I have an array, what page of memory or pages of memory does that array live on? Does it live on one page? Does it live on 100 different pages? I mean, yes, it depends on the size. But suppose I had an array of 1,000 elements. That array, if it doesn't live all on a single page, it lives on 2 pages. And those 2 pages are beside each other. So tell me this, if I am accessing the individual elements in my array in order, I'm going to walk over to RAM to get the page table entry for the 0th array index. And then when I go to access the first element of the array, I'm going to go get the page table entry for accessing the first element of the array, and the second element, and the third element, and back and forth and back and forth. But here's the problem. The page table entry I just retrieved 1,000 times was the same page table entry over and over and over. I keep getting the same piece of information. So it's almost as if I wasted all of those trips to RAM. Wouldn't it have been nice if I had some way on the MMU or on the CPU to store that page table entry, since I know I'm probably going to be using it again really soon? And in fact, yes, we have such a thing. That cache is called the TLB, or translation lookaside buffer. And you might remember TLBs from 251. Maybe you don't. I don't know. So the question is, what is this TLB? Well, the TLB is a very small, dedicated cache that is used to store information to be used in address translations. So you're looking at things like page table entries or segment table entries. And the idea is that the TLB entry will store the page to frame mapping. And then the MMU, instead of always going straight to the page table to get whatever it is you want, you're going to check the TLB first. Always check that TLB first. Always. Okay. So how does address translation actually work? So there are two implementations of this. The first implementation, of course, is called the hardware managed TLB. Now what's going to happen here is that the MMU is going to handle the TLB completely itself. So the kernel of the operating system is not involved with the TLB so much. So here's what's going to happen. When you try to perform an address translation on the MMU, we're first going to look up the page number in the TLB. When we look up the page number in the TLB, if there is a hit, that is, it is in the page in that TLB, then we are going to return the frame number and we're going to perform our address translation. So we didn't have to do anything extra. Great, right? So what, however, happens if there's a miss? That is, the page number is not in the TLB. Well, if it's not in the TLB, then we are going to have to go to RAM. And hardware will handle this, because this is a hardware managed TLB. So what's going to happen is we are, as the CPU and the MMU, we are going to go to RAM. We are going to grab the page table entry. We are going to insert it into the TLB ourselves. And then we will return the frame number, and the address translation will happen as normal. Now, what's interesting here is because the TLB is actually a very small piece of memory, it could be the possibility that when I retrieve my page table entry from the page table, that my TLB was already full, at which point we have to choose which of the existing entries do we kick out. And these are, of course, cache eviction strategies, and there are many, many different ones. Sometimes we'll pick the oldest one, sometimes we'll pick the least recently used one, sometimes we'll pick a random one, which is surprisingly effective, actually, but some strategy. All right. So there are some disadvantages to using a hardware managed TLB. One of the disadvantages is your hardware now has to dictate to the software, that is the operating system, what the format of the page table actually has to be. Because the hardware has to be able to go to RAM, and the hardware actually has to be able to read that page table entry. So it has to know where are the page bits, where are the frame bits, where are the use bits, where are the dirty bits, where are the bits that I actually want. So we're going to have our hardware dictate the format of our page table entries. And as a developer, you don't necessarily want the hardware to dictate the format of data to you, because what if in your particular operating system you need a few extra bits because you want to perform some other algorithm? Then that wouldn't necessarily be available to you. So hardware managed TLB, while it could technically be faster than the alternatives, the fact that it is restricting you to a certain page table entry format may be limiting to the implementation of the operating system. Trade-offs, right? So the alternative, of course, is to use something like a software managed TLB. And that is actually the most common one. It's what even OS 161 uses. And you know this because you've been getting panics about TLB entries, and they happen in the kernel. So what is that exactly? So what happens in a software managed TLB is that the MMU does not go to the page table ever. So the MMU instead is going to rely on the kernel of the operating system to keep the MMU familiar with what are the recently used page table entries. So this is how it works. It starts off the same way. We're going to check for this page in the TLB. If we can find an entry in our TLB with that page number, then it's a hit. We return the frame number and we proceed with the translation as normal. No problem, right? But it's where it's different is when you have a TLB miss. So on a TLB miss, the MMU raises an exception. That's it. Raises an exception. This is, shit. I don't know what this is. It's not in my memory. So, Kernel, you deal with it. Okay. So what does the kernel do? Well, when the kernel receives that memory exception, it's actually not going to be treated like a hardware interrupt. This is actually going to be treated more like a software exception. And so we're going to call the common exception code, and then common exception is going to save the trap frame. And then in MIPS trap, we would realize, oh, this is a memory error. And then we would turn our interrupts back on because we actually don't mind being interrupted during this process. And then we are going to call something called VM fault. And what VM fault is going to do is it's going to look at the fault address, and it is going to look up the page table entry for that fault address. And then it is going to, that is the kernel, is going to update the TLB on the behalf of the MMU. And the kernel then may realize that the TLB is full, and so the kernel will be responsible, of course, for fixing that. So the kernel is responsible for performing any cache evictions. Once the kernel is done updating the TLB, we will return, and the MMU will retry the instruction that caused the exception, and this time it will actually succeed because the entry will be in the TLB, so it'll have a TLB hit. Now, this actually brings up some really interesting discussions because now we have to ask ourselves, this is obviously quite costly. If a TLB miss causes an exception, and that causes the kernel to run, we know that that's not exactly fast. So we need to try to minimize the number of exceptions the MMU is throwing. So we need to make sure that the TLB is as relevant to the currently running thread as possible because we really want to minimize those exceptions that are being thrown. And this is why cache eviction strategies are actually researched quite a bit, is because whether it's caching for other purposes or caching for an MMU, we want to make sure that cache misses are minimized because the cost of a cache miss is quite expensive. All right. Now let's take a look at MIPS. So our MIPS hardware actually does use paging. So our sys161, which is our simulator, is actually a paged MMU. And it does actually have a TLB, and our TLB has room for 64 entries. That's not bad, actually, considering we don't do much with OS161. Now, each of those 64 entries is actually 64 bits, so it's 2 words. And if we look at the format of our page table entries, this is what they look like in the TLB. There is, in the high word, which is the upper 32 bits, that is where we store the 20-bit page numbers. So we've got 20 bits for our page numbers. Now, we don't necessarily use, by the way, all 20 of those bits. It's just to say we have up to 20 bits for said page number. Then we have in the highest bits of the low word, we have 20 bits set aside for the frame number. And again, we don't have to use all of those bits. Because pages are actually only 4 kilobytes. So if you Yeah, I mean, the page numbers and frame numbers here are going to be 20 bits, but if you wanted to use a different size virtual memory, you could in theory. So that's totally possible. So we've got 20 bits for the page number and 20 bits for our frame number, which is actually what we are using in OS 161. And then we've got a bunch of other information in our TLB entries. For example, we have a write permission bit called TLBLO dirty, which you're going to have lots of fun with on i3. We also have a valid bit. And then there's this one field here called the PID. Now that's a really interesting field, really interesting field. The PID field is not used. And so what could it be used for? So this field is meant to be used to store the PID or some kind of unique identifier for which process does this page table entry refer to? Because here's the thing. So when you do a context switch from one process to another process, that is, you're changing address spaces, the kernel, of course, has to update the MMU to let it know that, hey, here's your new information for your new page table. Okay. But what we haven't said is that you also have to clear the TLB out, because all of the TLB entries that you had prior to the context switch belong to process A. After the context switch, those process A TLB entries are completely wrong for process B. So to make sure that you don't start translating addresses for process B using processes A's cached entries, we have to clear the TLB. And in OS 161, it's actually a really funny function, and I'm sure some of you were probably really tempted to use this function. It doesn't do what you think it does. It's AS activate. So you might have thought that after I create an address space and I copy the address space and I attach it to my process, I should call AS activate to make it go. Except that's not what it does. It's the single worst named function in all of OS 161. AS activate clears the TLB. Now, that's not going to have any real impact on your assignment, but it will make things go momentarily slower, but probably not perceptible to the human. So here's the thing, though. Let's say I run process A, and then I run process B, and then I go back to process A. What if process B only put like 2 things in the TLB? But process A had 60 things in the TLB. But when I go back to process A, all of those 60 things are gone. So there's no cache affinity. There's nothing left behind. Wouldn't it be nice if when I went back to the original process, there was still things maybe in the cache for me? Well, that's what this PID field can be used for, is you could, in theory, use this PID field to have an additional check on the MMU to say, okay, this page number corresponding to this process. So you could have 10 page 15s, page Fs, in your TLB, but each one corresponds to a different process. And that way you can get some cache affinity out of the TLB. So that's kind of fun. But it also serves as a bit of a protection mechanism, because sometimes maybe you don't have the TLB properly set up. Maybe they're doing some kind of cache attack. But if you do not have the PID that corresponds to the PID of this TLB entry, then we can't do the translation. So it does also add a little bit of security. Now, what's interesting is this field exists on the TLBs for many modern CPUs you have in front of you. So AMD and Intel. And what's really interesting is that this field was not used until very recently. And I want to say it was 2017, but I'm not 100% certain. I think it was right around the time of Meltdown and Spectre that this field started being taken more seriously on modern CPUs. So these days, this is used on your CPU. But for us, it's not. It's totally ignored, so please don't use it. It's not supported in any way. But that's what it could be for. All right. So, to conclude with our discussion of paging, let's go over some of our things. So paging did solve our external fragmentation problem because every allocation is now exactly the same size. We do have a bit of internal loss, but if you are only you're only losing a few kilobytes per address space, so if you consider how big RAM is these days, I don't really feel that is particularly problematic, my opinion. And then we had the problem of the page table could end up being significantly larger than the amount of memory we have or the address space. So we introduced multi-level paging to reduce the amount of memory that we need for it. Now, one thing I want to keep in mind is the fact that just because you have a multi-level page table does not mean that your page table is guaranteed to be smaller than the single level equivalent. In fact, if you were using 100% of the virtual memory, then the single level table will in fact be smaller than the multi-level table, simply because there's no extraneous information stored in it. So there is a point at which the single level does save you memory. This doesn't really come up though, because our virtual memory is so large that nobody actually uses that. And the operating system itself can actually make some restrictions to make sure that nobody ever comes near it. Now, right now, we use on Intel CPUs, it uses 4-level paging, so 48-bit virtual addresses. 5-level paging is somewhat supported with 57-bit virtual addresses, and my understanding is the Linux kernel already supports that, so that's exciting. So the other thing is that because we have this multi-level thing, we actually have an additional problem. So we've talked about how always going to RAM to get the page table entry is slow. When you're talking about this for multi-level paging, this is where it gets really bad, because instead of going to RAM once per lookup, you actually have to go for each level. So on an Intel CPU now, without a TLB, each instruction translation requires a minimum of 4 RAM accesses, because you've got to go get the PTE for the first level. Then you have to go get the PTE for the second, the third, and the fourth. So actually using that TLB on a modern CPU is really, really good. It's going to improve our performance significantly. Like, we are really cutting down our memory accesses. So that's really fun, right? All right. So, it's time to talk about that which is known as dumb VM. So, if you have been wondering, why are there so many problems with the virtual memory or the memory implementation on OS 161? What is going on? There must be some mystery with this thing. Well, all right. So there are a lot of problems with the implementation of virtual memory on OS 161. For one, free doesn't do anything. Free doesn't do anything because how OS 161 keeps track of how much memory is free is it has a pointer. And it says, okay, you need to do an allocation. So it starts at the pointer and it gives you that chunk, and then it advances the pointer. But it never moves it back. So memory that you've technically freed never can be reused. Yeah, that's not good. Other things that are problematic. OS 161, when the TLB is full, do you know what happens? Kernel panic and die. It has no cache eviction. Spooky. And then, to top all of that off, a user program can actually overwrite its code segment because there's no read-write protection. So our dumb VM, which is our virtual memory implementation in OS 161, is actually quite restrictive. It doesn't work very well. Okay, so how is it actually implemented? Well, let's talk about that. All of those problems, by the way, that I've mentioned, you're going to be solving on assignment 3. So we'll talk more about those problems in detail later. So first off, we've already mentioned that MIPS, we're using 32-bit physical and virtual addresses. On top of that, we are also in a hardware level using paging. So we have a TLB. That TLB is software managed. However, OS 161 is actually using segmentation. And if you're wondering, how are we shoving segmentation down the throat of a paged MMU? Well, the trick is that instead of considering the limit of the segment as being the number of bytes, we're going to consider it to be a number of pages. And those pages are going to be contiguously allocated in physical memory. So instead of doing 7 individual allocations so that each page of a segment is mapped somewhere else, we say we need 7 pages for the code segment. So I get 7 contiguous frames of physical memory. And the page table, you don't have to create one because it's just a simple calculation. Of course, since OS 161 is using segmented memory, that means, and each allocation is going to be technically a different size, although a multiple of page size, we end up with external fragmentation and a number of other problems. So now let's actually look at the address spaces themselves. So here you have it. This is the address space structure for OS 161. So it has several fields. These fields are storing the information we need to know for where is the base, that is the low address of this segment in physical memory, where is the base of this address in virtual memory, and how many pages are each of the segments. So if we look at this address space here, we have an example. We have the code segment here, and the code segment corresponds to vbase and pbase 1. So you can see that vbase 1 is actually where in virtual memory does the beginning of the code segment start. And then we have pbase 1, which is where in physical memory does that segment start. And then n pages is how many pages, how many contiguous pages is that particular segment. And then we have vbase, pbase, and n pages 2, which are going to be for the second segment. So our address spaces only have 3 segments: code, data, stack. So you've seen we've got the information for code, we've got the information for data, and now we have the information for stack. So the question is, why don't we have all the same information for our stack? We don't have the vbase address for the stack, and we don't keep track of its size. What's going on here? We only keep track of, in the address space structure, the physical base address for our stack, and there's a reason for that. And that is because every stack is located in the exact same place in every single address space, and the size of the stack, that is the maximum size of the stack, is the same. So there's actually constants, I actually think it's a macro, inside of OS 161 that are used to keep track of the virtual base address of the stack and the size in pages of the stack. And for the record, the stack in OS 161 lives at the bottom of the stack, that is going to live at 0x7FFFFFF. So exactly in the middle of our address space. And the maximum size is 12 pages. So we can have a 48 kilobyte stack. Those are hard coded into the operating system. Please do not change them. Okay. So how does address translation actually take place? Because we're using segmentation. So how are we actually going to figure out which segment does an address belong to? Now, we're not using a traditional segment number where we separate the higher order bits to figure out our segment number. No, dumb VM. It has a big old if statement. So the first thing we're going to do is we're going to calculate the base and top for each of the segments. So base is the low address. So we grab those directly from either the address space structure, or you can get the low address for the stack by doing this computation here, which is user stack. And user stack has the following value. So that's like the limit. You're not allowed to actually write to this address as the user, but that would be the limit. And then minus dumb VM stack pages, which is 12, times the page size, which is 4 kilobytes. So that is going to give you an address that I will show you momentarily. Now, so that's our base address of our stack, and then we compute the top. That's the high address for each of those segments. So we have the top address is the base address plus the number of pages times the page size. And we do that for each of the segments, with the exception of the stack, where we know that the limit of the stack, the address, that is the high address, is actually just user stack for the stack. So once we've computed the bottom and the top of each of our segments, the next thing that we're going to do is we're actually going to check to see if the fault address falls in one of those ranges. So we first compare the fault address to the code segment. And if it's not in the code segment, we'll compare it to the data segment range. And if it's not in the data segment, we'll compare it to the stack range. And otherwise, we return an error code. Now, if it is in a particular segment, how we actually perform the calculation is to subtract the base address from the fault address. So we, in the kernel, are actually going to perform the translation. Now, we're not doing this per address, but we are going to do this on every TLB miss, where later we'll figure out what page this is on, and then we'll store that in the TLB. So we do fault address minus fee base, and then we add the physical base back. So this is going to compute, the subtraction computes our offset, and then the addition performs our actual translation. And there you go. That's it. Now you will find this code in dumbvm.c. And this function, this is in the middle to bottom of VM fault. So let's then take a moment and perform a few of these address translations. Because who doesn't want to do that? So let's do this again. I always like to pick on process A, so I'm going to pick on process A again. I guess it's process 1 in this case. There we go. So we're not going to do all the individual computations, but let's look at this first address. We have 400004, and I want to know which segment is that in. So we start by looking at the vbase, and I'm going to tell you, since the code segment is 8 pages, so I want to tell you a secret. So 4 kilobytes, we say that's 2 to the power of 12. If you were to represent this as a hex number, it would be the following. This is a good thing to memorize. So I know that my code segment goes from, make sure I got the right number of zeros here. There we go. Some lines appeared on my screen. Where did they come from? I actually don't know because I didn't touch that button. All right. So looking at this address here, I can see that yes, indeed, this address is actually in the code segment. So then I have to check. I know it was in the code segment, and I see that it's smaller than my base, or my top, so I know it's in the code segment. So I'm going to find the offset. And my offset here is going to be 4. So then I'm going to add to my offset the physical base, which is, so for the first address, this is what you should get. Not too bad, right? Fairly straightforward. All right, now let's choose another color. There we go. All right, so now we're looking at address, this 0x100091A4. So we can see very clearly that this is not a part of the code segment, but maybe it's a part of the data segment. So we go to the data segment and we say, okay, well, how many pages are you? Oh, you're 10 pages. So the data segment is going from something like this to that address there. So I can clearly see that my fault address is within that range, which means that this is in the data segment. So I'm going to compute the offset by subtracting the virtual base, which gives me 91A4. And then I add that to the physical base, which is 800,000. So for the second address translation, I'm going to get 0x8091A4. And everybody's happy, right? All right. Now, the next address, this is a trickier one. So I have 7FFF41A4. Now, I can see very clearly that this is not in the code segment and it's not in the data segment. So the question becomes, is this in the stack segment? So I know my stack physical base address and I know my stack top, but I don't know my stack base. But my stack base, since I know it's 12 pages, I'm going to subtract C1000 from my user stack, and that's going to give me my stack base, which ends up working out to the following. So I can see clearly that this address is within the stack. So I compute my offset, which is going to be 1A4, and I'm going to add that to my physical base address from my address space. So I end up with, I apologize, some of my zeros look like sixes. That's it's hard to write on this thing. Okay. So where do we go from here? So from here, we have one more stack address. Now it looks like a stack address. When I see something that starts with a 7FFF, I think to myself, that must be a stack address. But then I take a very close look at the final 4 digits and I realize that that's actually smaller. And so the last address is actually an exception. And I encourage you to try these same translations for process 2. Should be fun, right? Okay. So that is how OS 161 actually does the segmented translation. Now what's going to happen later on in VM Fault is we will actually figure out quite simply which page and frame that maps to, so that when we do the lookup, when the MMU does the TLB lookup, it will actually work out. And that's fairly trivial to do. Okay. But here's an interesting question for you. How did that address space actually get initialized? Like, who did that? And actually, the answer for who did that is, well, all of the information, aside from the stack, of course, for creating that address space was actually in the binary file. Because the operating system doesn't know how much code you have. The operating system doesn't know how big your data segment should be. But you, the program, should know. And who told you how big your code segment needs to be? The compiler. So our code, our binary program code, is of a format called ELF, so executable and linking format. It's very similar to the format from CS350. And when we compile our binary file, this ELF file, into that file, we will actually put all of the information we need to create the address space for this program. And I'll actually show you an example here in just a minute. So, and then what happens is inside of OS 161, when you actually do like execv and load the program, you'll see a function called load_elf. And what load_elf does is it reads the header from the binary file. And when it reads the header from the binary file, it can actually set up the address space for your program and populate it. So all of that information we need is right there in the binary file. Now, the stack is not a part of this. And the stack is not a part of this because the stack's initially empty. Or it has some arguments on it that were passed from the kernel. And another reason why we don't have the stack here is because the operating system typically dictates the maximum stack size. Ours is 48 kilobytes. Mac OS, Windows, and any version of GNU Linux, they're going to be around 1 to 2 megs by default. So it's not that big, but it is typically dictated by the operating system how big that stack's going to be. But the ELF file is going to contain everything else. So it contains the virtual addresses for the start of the segment. It contains the length of the segment. It contains information about where in the binary file you can actually find the data to copy into memory. It contains information about where is the entry point. Like, where's the address of main? That's in the binary file, in the header. It's also going to contain information like which of the segments are read-only and which ones can you actually write to. It'll contain information for debuggers and symbol tables and linkers and loaders. There's lots of information in that binary file. So our binary files actually only have two parts that we're using. We create a text segment, which is going to consist of the read-only data, and then we have a data segment, which is any other global program data. But our ELF file won't contain anything, of course, about the stack, or we simply won't use any of the other segments. So let's actually take a look. So I'm going to cross my fingers and hope that this actually works, because I have rebooted my computer. So maybe we will just run that. And then in root here, I am going to execute CS350 object dump. And there is actually a non-350 version of object dump, and you could do the same thing on your computer. And I am going to pass to it sort, which is one of the... And of course it's not working. This is the directory it's supposed to be run from. I don't know why it's being difficult today. Oh well, we're not going to worry about that too much. I'll get it working for next class. But what it's going to show you when we actually look at that is we will actually see exactly what segments there are in our ELF file, and we will see exactly where each of those segments have to go. I don't want to sit here and spend all this time trying to get it to work when every time Mac does like this major update, it breaks all of my my tools like DCC and GDB. It breaks them every single time, and then they change the default shell from bash to ZSH, and yeah, evil. So, the next topic. So we've seen how the address space for OS 161 very briefly, and again, I'll do the demo next class. But we've seen how our address space gets loaded. We've seen how the address translations work. And hopefully now you should see, whenever you see if you see a TLB miss on an address that looks something like this, you should be able to calculate where that TLB panic is happening. Because if you see an address, and this is, by the way, always where the code segment lives, and this is always where the data segment lives in OS 161, they're hard-coded values. So if you see addresses like this, you know that this is a user program experiencing a TLB miss. It is the user program. So what if you see, sometimes we have TLB misses, but they're in addresses that are above this one right here. So they're above user stack. What's going on? Well, we have our user program using virtual memory, but I want my kernel to use virtual memory too. Seems like a good idea, right? Let's have the kernel use virtual memory. Well, that's an interesting challenge, isn't it? Because the kernel is responsible for implementing virtual memory and managing it. So how is the kernel going to run while it's booting in virtual memory if the kernel is responsible for implementing and managing it? So we call that the bootstrapping problem. And then we have the sharing problem. So sometimes you have to copy data between the kernel and application programs, as you'll see in A2B. So if you have to do that, but every program is using the same range of virtual addresses, then how do you know which address space you're actually copying to? You don't. So we call that the sharing problem. So we need some way to actually make it so we can copy memory from one address space into another one, like the kernel. Sharing problem. Now, the bootstrapping problem tends to be solved by hardware. And for us, we are using dynamic relocation pretty much for our kernel virtual address translations. And again, this tends to be architectural specific. But for the sharing problem, and this does actually help with the bootstrapping problem as well, we are going to separate the user addresses for the kernel addresses. So this is not in physical memory, this is in virtual memory. So you may have noticed that I keep drawing the stack in the middle at this address instead of at the end like CS136 told you. So this is because that's how it is. It's not at the end of virtual memory. It's actually in the smack in the middle of it. Because what we have done is we have taken virtual memory, the address range, and we've divided it into two. The lower addresses are going to be for the user's process to use. The higher addresses will be for the kernel to use for its virtual memory. Now, this is actually quite interesting because now our user virtual addresses are different from our kernel's virtual addresses. And hardware can know that. And if the CPU is in an unprivileged state and the MMU tries to translate an address in the kernel because it knows about this split, because it's part of the architectural solution, then the kernel or the MMU can throw an exception because you don't have permission to access an address that is not in user space. So this is both for abstraction purposes, but having the kernel run in virtual addresses adds a level of security. So this is actually really cool. So now I can differentiate between a user address and a kernel address, and that's useful inside the kernel and it's useful in the hardware as well. So is this just an OS 161 thing? Actually, no. So OS 161 does a 50-50 split, and that's actually the most common amongst operating system is a 50-50 split. So if you're looking at Windows, if you're looking at Mac OS, if you're looking at any of the Linux kernel, we are doing a 50-50 split. So the low end of addresses are user and the high end of addresses are kernel. And you might have actually known that because if you ran any sample programs, like I had run here, let's see if I don't have it open, but I ran for you a little experiment before, and that little experiment, what it did was it showed you all of the different addresses of all of the things that we're running. So we saw an address on the stack, an address on the heap, an address of a global variable, an address of the code. And what you'll notice, especially if you're debugging with GDB, is none of the addresses are above the halfway point. And if you don't believe me, go write a bunch of programs to try to get an address outside of that halfway point that actually works. And you can't do it. You can't do it because the user address space is restricted to that low half. So this solves the sharing problem because now we can differentiate between them. And it also solves a bit of the bootstrapping problem because now the hardware can actually differentiate between user and kernel virtual addresses. All right. So I'm actually going to leave it there for today. We will review OS 161's virtual memory at an architectural level on our next episode, which is episode 15 next week. And then after that, we are going to talk about on-demand paging or exploiting secondary storage to permit us to have processes with large address spaces or more processes running than we technically have room for. So that will be on our next episode. Now I have one exciting announcement to make. And that exciting announcement to make is I believe we are actually going to have a guest speaker. I have managed to find a wonderful sponsor for them, and this will not take part during an actual episode period. This will happen at a separate time. It is not a required, you don't have to watch it. It's up to you. So I just need to set the date. And once I have a date set, I will let you know who our wonderful speaker is and what the topic will be. And how you will be able to participate, whether it's a live event or a pre-recorded event, we will let you know then. But I think you will find this individual very interesting, and he has some very interesting things to say. So I think it's going to be a lot of fun. So stay tuned to Piazza to hear more about once we get our speaker date set. All right. So, we will see you later.
It's in here. You told us Windows 98 would be faster and more efficient with better access to the internet.
It is faster, over 5 million times.